Hi guys, my name is Peter C. Dokpo Jr., mathematics instructor at the University of Liberia and your math tutor. In this video, I will be looking at the proof of some properties of differentiation, or we also call roots of differentiation. And in previous video, we did proof of constant rule, constant multiplier rule, sum or difference rule. And in this video, we want to prove the power rule. And to do that, we're going to use the first principle of derivative, or the definition of derivative, that has to do with the f prime of x is equal to the limit of f of x plus h minus f of x divided by h as h approaches 0. So we said this is the power rule. If x is differentiable, that is, if x is a variable or if x is a function that can be differentiated, and then d by the x of x raised to the power n, where n is any real number, then its derivative is equal to n times x raised to the power n minus 1. Now, so to prove this, we say let's take note of this binomial expansion, because we want to use it along the way. So what is the function that we are to prove or we are to differentiate? Because in here we have f of x, which represents the function, and here we have f of x plus h, which represents the new function when x is replaced with x plus h. So we told you in this bracket, it is the function, because it is this function you are about to differentiate to give you this result. So our f of x now will be, let's have it right there, f of x is equals x raised to the power n. This is our f of x. So if that is our f of x, then f of x plus h would just be equal to, now in this parenthesis right between here, this x now was removed and replaced with x plus h. So it has been replaced with x plus h. Likewise, on the right hand side of the equation, this x as well must be replaced with x plus h raised to some n. So now we have f prime of x is equals the limit. Now, what is f of x plus h? F of x plus h is just this expression, right? Now let's bring this thing right there. F prime of x is equal to the limit of f of x plus h is just this one, right? X plus h raised to some n. And then f of x is just x raised to some n, all divided by h, as h is approaching 0. So now our objective is to replace x plus h raised to some n, is to expand it using the binomial expansion. So we can select all of them, right? Either this expansion or this expansion. Both of them represents the binomial expansion in different forms as well. So let's take the second one for instance. So this expression now is being replaced with this binomial expansion, which is x raised to the power, I'm going to bring it down small. So f prime of x is just equal to the limit. Now this one, x raised to the power n divided by 0 factorial. Now we know that 0 factorial is just 1, right? Plus n x raised to the power n minus 1 times h, all divided by 1 factorial is just 1 as well. Plus, this is n minus 1 divided by 2 factorial, which we will get that later, n minus 2 h raised to the power 2 plus in the next term. So we don't have to go 3 terms, 4 terms, 20 terms, and so forth. We can basically just take 3 terms. Let's say for the sake of understanding some patterns, take at least 3 terms. So let's take the first 3 terms, 1, 2, and 3. So from these 3 terms, we can generalize a kind of pattern. So we have plus, dot, dot, dot. It means it continues, right? Minus x raised to the power n divided by h. Or we can say we use a division sign. So this whole thing is divide h. H approaches 0. So f prime of x now, we further simplify it now. We have this to be our x to the power n plus, this is our x to the power, let's say n, x to the power n minus 1, h plus n minus 1 all over 2, x raised to the power n minus 2, h square plus dot 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 x to the power n, all divided by h, as h is approaching 0. Now what do you observe? What do you observe? The first term, x to the power n, cancel the last term, x to the power n. So we'll just be left with all of the remaining terms between here. So let's erase. Okay, I can erase this one. It's not too important. We just use it for the problem. So we can get rid of it now. Okay. So we have f prime of x to be equal to the limit. Now what is left is n x raised to the power n minus 1 times h plus n times n minus 1 all over 2. 2 factorial now, right? So we know 2 factorial is just saying 2 times 1. So x raised to the power n minus 2, h raised to the power 2 plus dot dot dot. All this expression, all this entire thing just divided by h, as h is approaching 0. Now mind you, your primary objective is to get rid of h from the denominator so that you can be able to apply the limit, because when h remains in the denominator, applying the limit will take the entire thing to an undefined statement, because if 0 is placed here, it means that it's undefined. So we have the limit. So what we can do is we can see our best to factor out h, because we're seeing h here, we're seeing h here, right? So we can bring out h. And what will be left with here is x to the power n minus 1. H is no longer here. So the first one is n, x raised to the power n minus 1, plus this second n minus 1 times x raised to the power n minus 2. And then this h times h, 1 is already outside, so you left with h plus dot 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 divided by 2 as h approaches 0, all divided by h down here. So this h cancel this h. So what we will be left with? We'll be left with the limit of n x raised to the power n minus 1 plus n minus 1 all over 2 x raised to the power n minus 2 times h raised to the power 2 plus dot 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 as h approaches 0. So since there is no denominator called h that was always taking the problem to 0, or an undefined statement, we can now apply the limit. So wheresoever we see h, we can now replace h with 0. So the first term there is n x raised to the power n minus 1 plus the second statement is n minus 1 all over 2 times x raised to the power n minus 2 times h now, which is 0 raised to the power 2 plus dot dot dot. Now notice that h was increasing in the problem from h to the power 0 to h to the power 1 to h to the power 2, h to the power 3, h to the power 4, and so forth. So beginning from this term to the rest of the terms, all of those terms beginning from here will all end in 0. Because if you put 0 here, this whole thing will go to 0. The next term will go to 0. The next term will go to 0. Infinitely, all of them will go to 0. Therefore, f prime of x would just be equal to n x raised to the power n minus 1, which is now the derivative of the function x raised to the power n is n x raised to the power n minus 1. So you have been proving that the derivative of x raised to the power n, where x is a differentiable function and n is any real number, its derivative is equal to n x raised to the power n minus 1. Thanks so much for watching. See you in our next video.